So you could ask, there's one funny question you could ask, which is, I think, what you're asking, which is, look, suppose the world really is linear. And you told me that OLS gets me the right coefficients. So I'm getting that's on average unbiased. So in that world, why wouldn't I just use estimation? If I can, isn't the estimator the best predictor also? Like, what's going to be a better predictor than having the right coefficients on average? That'd be a question you could ask. Totally reasonable. More, yeah. We'll come back to the second part of your question in a second. But that's the first question you can ask. So let me give you an example, and I'm curious what you guys think. So you run OLS, and what you get, let's ignore the constant term for a second. Let's suppose that what you get is a coefficient here of 10 with a confidence interval of 0.5. And then on this beta 2, yeah, 10 is fine. On beta 2, you get a coefficient of 25 and a confidence interval of 200. OK? Unbiased estimator, OLS is unbiased. Someone says to you, you've done all this work. It turned out I only gave you half of my data. I want you to do whatever you want. I don't care. It's none of my business. Just hand over a linear function of x1 and x2. I'm going to compute that function on each of my other data points, take the difference between the true y and what you predicted, and depending on how close you are, you'll get paid out. Your OLS has produced this. How many people would say, I'm going to hand over the vector 10x1 plus 25x2 as my predictor? No one. But it is the unbiased coefficient. We just all agreed. Why don't you want to hand it over? So much variance. Which in turn means what? I have some bad news for you about the world and life in general. We'll discuss after class. No. It's clearly not good. It's clearly got a lot of variance. But what about the variance bothers you guys? Yeah.
It's not as relevant to the prediction.
Yeah, we're so used to doing hypothesis testing, you're tempted to say maybe that thing doesn't exist. It's a 0. I can't reject 0. So I think that part of that intuition you have from the confidence interval is exactly that intuition. I can't reject 0. So if I can't reject 0, why am I predicting? Why am I using this thing at all? So one intuition you could have here is, gee, I can't reject that x2 doesn't matter. Maybe I should just leave it out. So for example, you might be tempted to leave out x2. I don't think you want to do 10x1. Why would you not want to do 10x1? It's hard to do a regression in your head, because x1 and x2 might be covariating. So if you're going to leave x2 out, you should run y on x1, get the new coefficient, and put that in. Does that make sense to you guys? OK. So, let's think about why you would want to do that. I think the reason you'd want to do it is because you have now introduced bias into your predictor. Clearly 10x1, or not 10x1, whatever beta 1 OLS x1 is clearly a biased predictor. We all just agreed, because that's not blue. But on the other hand, you get rid of all of this variance. What is all this variance? You know, if you were to run this regression again on another data set, you are going to get a coefficient on x2 that's somewhere between 225 and minus 175. That is a lot of variance you're putting in to your predictions. So the essence of this, why estimators don't necessarily by themselves make good predictors, is estimators have only one goal. They must be unbiased. Conditional on being unbiased, they lower variance. So, but prediction is not about conditional on being unbiased, lower variance. It's make the best prediction possible. So that's what people often call the bias-variance trade-off. What's misleading about the bias-variance trade-off is that actually the difference between estimation and prediction runs even deeper. which is, okay, I've got these two variables. Well, I mean, why linear? Let's throw everything into the mix. Let's do a nonlinear function. Let's put a bunch of interactions. Let's discretize the thing. Let's throw it all in. You wouldn't act in such a willy-nilly way if what you wanted was to get meaningful coefficients, because you're now putting in a bunch of variables that you might not even know what they mean or have any value. But if what you're trying to do is to figure out what in the signal of x's add up to y, you'd have a much freer attitude towards functional form. So one reason estimation doesn't become prediction is estimation doesn't do the bias variance trade-off. But the other reason it doesn't is because philosophically, it's always and almost always of the form, the world comes from this thing, or this is what we're trying to approximate the world with, what would be my coefficients there. In prediction, it's almost of the form, I want to allow as flexible functional form as I can. So if you look at these prediction contexts, it'll be like people who just said, well, I took a decision tree, I took a random forest, I did an ensemble between that and the nearest neighbor. It's just, everything goes into the mix. That's also the reason prediction doesn't really make for good estimation. Because once things get so high dimensional, the predictor is never telling you that these are the variables that matter. It's just telling you I found one representation that does pretty well at prediction. Does that make sense? So let me show you in the x1, x2 example why it doesn't go this way either. It doesn't go this way either because it's going to require something beyond my graphing skills. So this is beta 1, beta 2. Suppose I see a coefficient here. That's my estimated OLS coefficient. Then I have a standard error. One way that standard error could reflect itself would be this way. There's just a circle around it. But as you know, when x1 and x2 are covarying, these confidence intervals you see individually do not reflect their joint distribution. So for example, you might see a world that looks like this. What is that telling you? That's telling you, I have no idea what the coefficient on beta 1 or beta 2 is. But I know that the sum of them is very, very stable. For prediction, this is a dream. It's great. Isn't that awesome? For estimation, this is a nightmare, because it's telling you, I exactly cannot tell whether it's beta 1 or beta 2. Estimation is all about adjudicating between the two variables in your data set or the four variables in your data set. Prediction is about extracting their joint signal. So in this case, look what would happen at your standard errors on beta 1. It would be super wide, because that's the signal. And your standard errors on beta 2 are super wide. But your standard errors on, and this is where my geometry fails, x1 plus x2, is that right? Yeah, that's got to be right. On x1 plus x2 is very tight, because it's saying one of them is doing the work. I just can't tell which one is doing the work. So estimation is in the business of adjudicating between the variables that you have to figure out which one is doing the work. Prediction is in the business of saying, I'm just going to add them up and do the work. Does that make sense to everybody? OK. Any questions about this?